Welcome to our study on Kolmogorov Arnold networks under TinyML constraints, focusing on state of charge estimation for electric vehicles. This research aims to enhance the efficiency and accuracy of battery management systems in EVs. The transition to electric vehicles is crucial for sustainable transportation, reducing emissions and addressing charging challenges. Battery management systems are vital for accurate state of charge estimation, optimizing energy use and reducing costs. Tiny machine learning offers promising solutions for real-time inference and improved transparency. Our objective is to develop and evaluate a Kolmogorov Arnold network model specifically designed for state of charge estimation in electric vehicles, with deployment on TinyML platforms. This approach aims to improve the precision and efficiency of battery management systems. Our proposed approach involves a comprehensive process starting from data collection and cleaning, followed by variable selection, data segregation, and model design. We utilize Python for model conversion and evaluation, and hardware evaluation is conducted using various microcontrollers to make predictions. We address two key research questions. What computational resources are required for training and the accuracy of MLP and KAN models in terms of mean squared error? And, what are the microcontroller resource requirements for each proposed model, including memory utilization, inference time, and power consumption? Our dataset comprises battery and heating data from real driving cycles, encompassing 72 driving trips, 467,701 lines, and 28 columns. This extensive dataset allows for thorough analysis and variable selection, crucial for model accuracy and reliability. We compared two models, the Multilayer Perceptron, MLP, with 100 epochs and the Kolmogorov Arnold network, KAN, with 2,000 steps. Each model has distinct architectures and optimization strategies, tailored to enhance performance in state of charge estimation. Deployment involves testing on various development boards, including Arduino and Raspberry Pi models, each with different clock speeds, RAM, and flash memory capacities. This diversity ensures robust evaluation of model performance across platforms. In offline mode, we evaluate models based on time taken for training, energy consumption, CO2 emissions, file size, and mean squared error. These metrics provide insights into the efficiency and environmental impact of each model during training. Online mode evaluation focuses on energy consumption, flash memory utilization, RAM memory usage, and inference time. These metrics are crucial for understanding the real-time performance and resource demands of the models on embedded systems. Our offline metrics results reveal differences in time, energy consumption, CO2 emissions, file size, and mean squared error between MLP and KAN models. The desktop configuration used for testing includes an Intel Core i9-12900K, 64 GB of RAM, and an NVIDIA GeForce RTX 3080. The mean squared error histogram provides a visual comparison of error distribution between MLP and KAN models. This analysis helps in understanding the accuracy and reliability of each model in predicting state of charge. The online metrics results for the KAN model show variations in energy consumption, memory flash, RAM usage, and inference time across different devices. This data is essential for assessing the model's efficiency in real-time applications. Similarly, the online metrics results for the MLP model highlight differences in energy consumption, memory flash, RAM usage, and inference time. These insights are crucial for evaluating the model's performance in embedded systems. In conclusion, while MLP offers faster training and lower error, KAN provides smaller files and faster inference. The choice between these models depends on system limits, whether prioritizing efficiency or compression. Future works will explore hybrid MLP-KAN architectures, evaluate across multiple datasets and TinyML platforms, and integrate advanced quantization and optimization algorithms to further enhance model performance and applicability. Thank you for your attention. We appreciate your interest in our research on Kolmogorov Arnold networks and TinyML for electric vehicles. For further inquiries, feel free to contact us via the provided email or social media links.